وعليكم السلام.
Okay, welcome back to the class. So today, ya shabab, we are going to get to the end of chapter 11, and let me turn on the cam here. So we'll finish chapter 11 today, and I was honestly thinking that we might be able to start chapter 13, but we will not. I think similar to the other section, but that's fine. Inshallah, next class we will start chapter 13, which is about gearing. So that's a different interesting topic. Okay. So I'm gonna announce also the quiz, inshallah, later. So to continue the discussion on the bearing, and in connection to what we discussed before, you will see that there was a question by one student, I think from this section, last class, when we had the idea of a bearing, which is below, or let's say we picked a bearing and the bearing rating was a little bit below what was the desired load, and we said that's fine. So someone asked, when do we know if this is fine or not? So in general, when we talk about the assessment of bearing, we will have to think about different aspects, like the reliability, which was the discussion I just talked about, the load, the life expectancy, and then we have the shoulder. Shouldering is also very important for mounting the bearing, and we'll talk about it inshallah today. The journal finish, which is basically the shaft on which the bearing is going to be mounted. The housing, which is housing the bearing, and the lubrication, as well as the preload, which are some items that we will discuss by the end. But speaking about the bearing reliability, what we can do is the following. Remember one thing: when most of the time we design problems for selecting a bearing by determining what is C10. So in the previous problem where the question was asked, we determined C10, the calculated one, as 12,195 Newton. But when we went to the catalog, what did we get? We got a C10 which is equal to 12,100 Newton. And we said it's okay. We said it is okay. So the idea here is that most of the time when we go to the catalog and we pick a bearing, it will most likely be higher than what we have in the calculation, which is most of the cases, and in some cases like this one, it was lower. So you are actually not getting what you wanted exactly. You are getting a little bit less or more. That will affect the reliability. And this was the question: should I go with it or not? So if you recall the equation for the reliability, the equation which relates the reliability with the desired load and application factor, the catalog rating for radial load, the Weibull distribution factors, and the type of the bearing, which is a cylindrical or a ball bearing. This equation, we can solve it for R. And when we solve it for R, we are actually going to determine the rating based on the parameters that we have. So if you recall, this is just, I am trying to be helpful over here, and I brought up the example for you. This is not the question that we have here, but it says.
Yeah, doctor, is this section for both tapered and ball both, or is it only specifically for tapered?
Which one? This one?
This one, section 1110. Yeah, it's for both bearings, right? Tapered and.
Yes. This is for both now. We are talking now about ball bearing. We'll talk about roller bearing. The differences are minor. So, so what happened over here is that we will see that in the example 11.3, which we did long ago, okay, we had a load FD, which is equal to 413 pound force. We have AF, which is 1.2, and we have a reliability of 0.99, ND, which is 300 revolution per minute, and LD, which is equal to 30 kilo hours. That's what we had. And what did we say? We said this is a roller bearing. So there are balls bearing. This is the ball bearing. So with the Weibull distribution factors are there given to us. And what did we do? We found XD, and then we found C10. Now, based on this problem that we solved long ago, we picked a bearing which is 02, that's series 2, and 40 millimeter. The 40 stands for the bore size. Okay? Now, what happened is that, which is very common, is that for some reason, is it fatigue? Is it yielding? Is it standard sizing for a sleeve or a gear or whatever? We ended up using 70 millimeter. Series number 2, but 70 millimeter bore size. Now, what does that mean? Again, I brought you here table 11.2 for deep groove ball bearings. And what we solved the problem for, which is 11-3, is that we found that the load, be careful, when we found the load here, 6,696, that was in pound. And if you convert it and get the nearest, you will find that this bearing, which is rated for 30.7 kilonewton, this is in kilonewton, is good. Now, what did we use? We used 70. Why? The bore size. We need 70. And as I said, I'm not just going to repeat again and again. There are many reasons why we end up changing the size of the diameter. So that will give you double the rating. That's 61.8 kilonewton, the capacity. So what happens is this. If you want to know the reliability, the current reliability, you take the 61.8 because you use the bearing with this catalog value, you convert it into pound force because when you apply the equation for the reliability, you are using 413 pound force. So you need to be consistent. The live measure is here. This is the rated value, C10, over here. And then the Weibull distribution and so on. So what did we get? We got 0.99963. That's the reliability. Of course, this is expected, and it is much higher than what? 0.99. Now, remember one thing, ya shabab, over here. The wording, it says it is much higher. Huh? Why? I mean, in the end, somebody would say 0.99 is almost 1. 0.99963 is also almost 1. So What is too much over here? Well, just think about it. I can ask you to go home and keep changing C10 to higher value, higher value, higher value. Keep changing it. Same load, everything is the same. And you will see that this is just gonna increase a little bit each time, a little bit. And you can think of it, we doubled the rating. Previously, we used 40 millimeter with a capacity of 30.1 kilonewton. And what did we get? We get 0.99 reliability. We doubled, ya shabab. We doubled the force capacity to 61 kilonewton. And how much did we get extra? We got 9963. So we got 0.009963. So that little addition in the reliability, you may underestimate it. But look, you have to push double in order to get only this. Yet, it is considered too much compared to 0.99. Did you get it, ya shabab? So that's when we talked about it in fatigue. And we told you, if you recall, in fatigue chapter 6, we told you, if you want to have a KF in the endurance limit to be increased, to be buoyant, if I'm not mistaken, was it 0.9, I think? Yeah, was it 0.9? And then the reliability, this factor was like buoyant, it was very big. But if you want 99.99999, like 5 nines after the buoyant, you need to multiply the endurance limit by nearly 50%, if I'm not wrong. I don't recall the number. So you have a 100 kilonewton, let's say, endurance limit, and now you need to pretend that you have only 50 just to secure a reliability of 0.9999. Can you imagine that? I just want you to understand the magnitude of this thing. So this 0.009963 is not easy. That's why it is too much to get. Understood, ya shabab? I hope so. Now, what happened if we have a tapered roller bearing? Now, if we have a tapered roller bearing, then we can use the same equation. Yeah, just keep in mind that the Weibull distribution are those. X0 is 0. We talked about this. And you need to remember that A is 10 over 3. Yeah? So you can just use the same equation. So if we go back to the problem that we solved in the last class, if you recall, this is the argument I was talking about. We found by calculation that C10 is 12,100 Newton. Okay? And then we said that the reliability was, I mean, let me show you this. I need to go back just to convince you why the solution did that, okay? So if you go back to the question, it says that if the reliability of the bearing set is to be 0.99, the bearing set, right? And then we said that the reliability goal is supposed to be the square root of 0.99, which is equal to 0.995. That's what we said. Okay. So if we go here and look back to this problem, what did we do? We picked bearings, okay? And those bearings, which have a cone and cup as these, if you go to the catalog, then you will find that C10 is this much. Right? Now, when you go and use the equation, this is XD. Okay? Remember, X0 is 0. So in here, we have this is the equation over here. So this is theta. And then we multiply it by C10. And then AF divided by AF multiplied by FD. Now look, this is C10. This is the application factor, and this is the load. I hope, ya shabab, that you remember that this is FD. It was 4,938. If you got this confused, go back and check it in the solution. This is what? B, and this one is the A. Okay? This is not 1 over B. This is not 1 over A, because we're solving for A, not solving for C. If it is C, then they will have the reciprocal. Now, how much did we get the reliability? We will get the reliability as how much? 0.99479. Good. So, is this good? In the solution, we said, yes, it is. And the question was, how? This is less than the goal. The goal, which is RD, was square root of 0.99, which is 0.995. Yeah? So what happened over here? We said, that's okay, because the client, you can't force the client. The client said, I want the reliability set supposed to be 0.995. If the client told you, I want both bearings to have a reliability not less than 0.995, then that's okay. That's okay. Then this is not going to be the right answer. We need to change the bearing. But it says I want the goal. So if I continue and I find the reliability of the other bearing, its reliability is much higher. Why? Because it is a tapered bearing with the same capacity, but the load acting on it is much less. And in that way, if I multiply both reliability, how much do I get? I get 0.994. Now, this is more than the reliability goal. This is
Can you explain again in which situations we multiply and in which situations we take the square root? Because here we multiply.
Yeah. Remember, maybe I explained it in a way that confused you. Look, the reliability for two bearings, okay? A and B. So this is the reliability of the set. Okay? The set. It's like if I put two bearings right now in a machine, assume that the machine, all of its component, we are not worried about their reliability. Okay? Let's assume they have 100% reliability, although this is imaginary, but let's assume that. And the only thing that may cause that machine to shut down is the bearing. Okay? And then I told you I have bearing A with a reliability of 0.99 and bearing B with a reliability of 0.97, for example. Then if somebody asks you, what is the reliability of the entire machine with respect to bearing? You multiply both reliabilities. Right? So what happens over here? The reliability goal, remember, I'm going to show you one thing here. Look, I'm going to go back to the question over here and look carefully. When we say the reliability goal, we said that this is RD, which is equal to 0.99, which is equal to 0.995. What did we call it? We call it the desired reliability. RD is what goes inside the equation. For what? For one particular bearing, not for both. One particular bearing. So we take the square root of the reliability set in order to assign it for the bearing itself, one bearing. Do you get that?
Yes.
Okay. Now, but what if I picked two bearings like here? I picked two bearings and each one has its own reliability. This is RA and this one is RB. So we go back to the old equation which says that the reliability for the set is the multiplication of both RA and RB. Yeah. Now, this reliability is supposed to be compared to the one which the client asked. The client asked for 99%, 0.99 for the set. So what did we get over here? This is supposed to be compared with 0.99. We got 0.9945558. All of this is considered much more than this. So we are good. And that's the reason, listen, that's the reason why in the question it says, oh, the reliability of bearing A alone is less than the goal, less than 0.995. It's less. It is 0.9947. But we said it's okay. Why? Because the client is focused on one thing. He said, I want the reliability set to be 0.99. As far as the reliability set is 0.99, I'm okay. Of course, this is not always the case. Some other client will tell you, no, I want them both to be not less than 0.995. And that's another thing. You understand? Any other question, ya shabab? Okay. Now, in the next problem, okay, I would rather not honestly consume the time on this. It's very straightforward, but it is the kind of questions that I probably would guess that if I bring this in the quiz or in the exam, like 90% of you will not solve it right. Why? Because it's weird. We spend 2 weeks and one lecture, and today is the second lecture of the third week, talking about bearings, and always have radial load. Actually, we were arguing whether in some condition we have radial load and in some other we don't. Here, weirdly enough, there is no radial load, there is only thrust load. And it's just, I am pretty sure that you will not feel comfortable. And if I would predict student behavior in this problem, this kind of problem, believe me, somebody, if this is an exam, somebody is going to invent a radial load by one way or another. Why? Because that's what you got used to. And you will never give up that. You want a radial load, whether it is there or not, you are going to force it in the problem. And that's why this problem is interesting. So in this problem, what do we have? We have, in summary, we have FAE, an applied axial or external axial load, if we want to call it, which is 8,000 Newton. We have ND, which is 950 revolution per minute. And we have the desired life of 10,000 hours. The expected shaft diameter is so the diameter is 1 inch. 1 inch is 25.4 millimeter, as you probably know. The reliability goal, you get that? The goal of the reliability. The goal of the reliability is what, ya shabab? Is what we used in the equation, which means the reliability of the bearing supposed to be 0.95. The application factor is equals to 1, and we want to find a suitable ball tapered bearings for both A and B. Now, first thing first, there is no radial load. There is only a thrust load. And this is where things become a little bit, like different, not as we used to. So if you recall, with tapered bearing, we are, designed to, understand that there is a bearing which will carry the thrust load, and there is a bearing which will not. The bearing which will carry the thrust load will have two forces acting on it. The 0.4, the radial load, plus K multiplied by an axial load. Now, what we did before is that we said that if you look at this is the axial applied load. Now, interestingly, in the back, just last class, we said this bearing will be subjected to two radial loads. This radial load will generate an axial load and a radial force. Okay. And this one will have a radial load and an axial force. And then what did we say? We said combine this and this and to one force against the blue one. And that's how would we know which bearing is going to be squeezed. And thus, it is going to be the bearing which will have to handle both radial and thrust. Well, all of this discussion is meaningless here. Why? Because there is only one thrust load and it is pointing toward the bearing on the left. So this bearing is bearing A. Interestingly, this means that this bearing will carry all of the thrust, and bearing B will carry zero radial load, zero thrust load. It's just sitting there alone, doing nothing. That's where it gets weird. So if we do that, and you believe it truly, then you will know that if RA is the same as if RB, which is equals to 0. Yeah. This is it. Is equals to 0. There's no radial load. So, and if there is no radial load, remember, the induced load because of B is equal to 0.47 FRB divided by KB is equals to 0. And the reduced load FIA is also 0. And in that case, you will end up with the axial load at A is the same as the axial load applied at the shaft. What is the reliability? Both of them should have a reliability of 0.95. We can use that right away inside the equation. Now, since bearing A will take the thrust, based on our mechanism, if you recall, we said before that the bearing that will take the thrust will have an equivalent force, which is equal to 0.4 multiplied by the radial load plus some K multiplied by an axial load. That's what we said. So if you look in here, this is 0.4 FR is 0. And then we have Ka multiplied by this. Now look, this is the axial load coming from bearing B, the induced, and from the external. But there is no induced axial load. So we ended up with FAE. So what is the end result? This is 0. This is 0. We'll end up with Ka equals to FAE. Now, to make it easy, be careful on us. I want you to remember one thing. Do you, ya shabab, recall this figure? When we said the bearing, as we increase the thrust, goes like this, and then we said that this is the line with intercept x and slope equals to y, right? Now, when the slope equals to y, equals to 1, it means that I have an equation like the famous equation y equals to x is basically like this. It's an equation where the intercept c passes through the origin and the slope is 1 such that x is always equals to y. Is that right?
Yeah.
Oh, okay. Now, what can I do here? I am equipped with a tool which tells me if you have a tapered roller bearing, you should find FE, okay? And then when you find FE, go and assume it to be FD. And when you find FD, plug it inside the equation to find C10. Is that what we did? C10 correspond to a force, which is a catalog value for 10th percentile radial force. So when I go to the table, I don't look at the thrust. I look at the radial force. I say, okay, I got it over there. That's a radial force. And I should be fine. Now, in here, we don't have even a radial load. We have only thrust load. So what did we do? We said, okay, the best thing, what if I find C10 for a radial load, but the thrust load is not what I want? What if that's the case? Because K is the slope. And if you imagine that this x-axis is what, ya shabab? The x-axis is the axial, the y-axis is the radial. Your I, C10, is for radial, and you want an axial. So what do? By starting Ka equals to 1 in this situation, you are actually saying, I want to find a radial load in the catalog which will give me a bearing which carries almost the same thrust load. The radial and thrust are almost the same. Why? This is going to make it easy for you. When you get the radial load, you will know the thrust load will be similar to it, very similar, very close to it, and you will be able to pick a bearing which will carry this thrust that you have in hand. So,
Doctor, is this like the situation when we are before E in like the ball bearing questions?
yes, that's it. Okay. Okay.
Okay.
All right. What? Can you repeat the question again? Wait a second.
Yeah, I said, is it like the ball bearings part where if we're before E, FR and FA are almost equal, and after we cross E, we have to increase the thrust value. Sorry, FT and FR are equal to each other.
I got you.
Before E. Yeah.
I got you. I got you. Well, what happens is that That's not the case though. Why? Because before E, all right? Let me see. No, not that's the case. Sorry, I said yes, but this is wrong. Before E, the curve goes straight line. That's the curve straight line is not the same as a curve which is an inclined and with a slope y equals to 1, which what we are saying right now.
Okay.
Okay, so this is not. So you will see now. In a minute, it will appear to you. So this is Fe, A, the equivalent the equivalent radial load acting at A, which is 1, the K multiplied by FAE, which is 8,000. The radial loads are 0 for bearing B. And now what do? We put the 10,000 hours multiplied by 950 revolution per minute, multiplied by 60, divided by 90 million revolution for Timken, because the rating for tapered bearings and the catalog provided in the book is for Timken, and that's what we got XD. Now, when we got XD, we substitute it here. Okay, these are the Weibull parameter, and this is what, ya shabab? This is 1 over B and 1 over A. Okay, so it is 10 over 3 becomes 3 over 10, and 3 over 2 become 2 over 3. And now look, what happened when we get C10? This is C10. Now, when we get C10 over here, what does it mean? It means go to the table. I want to show it to you over here. First, make sure the bore size is 1 inch, which is 25.4 millimeter. Down is 1 inch. Second, K is almost 1. Yeah. Third, what was the force over here? C10 is 16,159. So the catalog value for this bearing has higher than that, which is 18,400 Newton, and C10A, that's a C10 axial, the rated axial load, okay, for this bearing is 17,200 Newton. All right, so, and this is it. That's the value over here. Did you get this?
Yeah.
All right. So, so next, ya shabab, is to go and calculate the reliability. So if we want to calculate the reliability, we need to put XD. Look, these are the Weibull parameter. This is now what, ya shabab? We are using the thrust load catalog value, because the load that we have is only a thrust load. Okay, and what happened over here? If we put this, notice that if D for bearing A is equal to what? 8,000 Newton. Was it in Newton or in bound force?
Newton.
It was, yeah, 8,000 Newton. So when we do that, what did we get? We get a reliability of 0.963. That's more than the goal. The goal was 0.995. Okay? No, this is, no, 0.95. The goal, what is it? Let me check the question. Yeah, the goal was 0.95. Okay? So this is more. Why? Because we have a load which is like 16,000 something, and we put a rating of 17,000. So we got a little bit higher reliability. For the other one, the load over here is 0. So you can imagine that if you have 17,000 divided by 0, it's going to get you an infinity. This number divided by infinity will push this to 0, and you will have a 100% reliability. Well, of course, there is no loading acting on it. So the combined reliability now is the reliability of bearing A and bearing B multiplied by each other, and this is what we got. Understood, يا أخوان?
Yes.
Okay. Now, there are a few other things that we need to go over with respect to the bearing. So I'm just going to talk about them briefly over here. I would encourage you, ya shabab, these are the kind of situations that you will see in the industry. And I know some of you, or maybe the majority of students, think that we are teaching you stuff that you don't use in the industry. But if you go and read this book, especially the writing, you will find a lot of information that are actually very practical in the industry. Also, I would like to tell you, and you know this more than me, if you found any information that you think you are not familiar with, go and search it. This material of bearings and gears is very popular. You can see a lot of videos on YouTube and the internet. So in here, for example, we are talking about the matter of fitting the bearing. So we have an annulus over here. So we want to make sure that that annulus, for whatever practical reason there, will not be bigger than the outer diameter of the bearing, so the bearing can sit from this side. All right. Also, we have the shoulder here of the shaft, which is also very important for placing the bearing in its position. So you want to make sure that the sizing for the other part of the machine, like the housing, the like here, the outer diameter, the big diameter, the small diameter, are all aligned with what's supposed to go with the bearing. Similarly, if you have a tapered bearing, we all know that we have here like dB. Look at it from the back, this diameter, as well as this diameter, as it is explained in the textbook. You want to make sure that these diameters are within the seating arrangement for. So if you put the bearing from the back or the front, you want to make sure that these diameters are within an acceptable tolerance and size with respect to the shaft and the shoulder. Okay. You need also to understand that in most of the bearings, especially in industrial application, they need lubrication oil. So they, like a turbine or a pump, is equipped with a whole system with a pump and storage and filtering and cooling where oil circulate. So you want to, just here it says that you want to make sure that you need to keep in mind that this circulation of oil means you need to supply pipes, tubes, to go, one takes the oil out and push the oil in. That needs to be considered while fitting up the whole thing. Now, look, with respect to lubrication, ya shabab, we have two types. One is called the grease, and these are some of the recommendation when to use the grease, and the other one is the oil. The grease is more viscous and than oil. Oil is running, okay, and viscosity is different than the grease. And you will see that this is also related to some other issues. I'm going to show it to you. But for example, for mounting, look, in this way here, this is an example where they decided to thread the part of the shaft in order to what? To screw this ring over here. whatever it is called, just to place the bearing and force it against the casing. So this is the same whether left or right. In some condition, this part is not there. This threaded part is not there. And then what they do, they have other ways. Look, these forces, other ways. There is a casing or a turning ring, any other arrangement to make sure that the bearing is being securely locked within. Look here for a tapered bearing. You can also have different mechanism like these here. These then look like washer. These one with this, ya shabab, I want to show you. Just we have like 1 minute. With this arrangement, this is usually associated with with labyrinth seal, which is very common in high speed application where the RPM is too high. This is the enclosure. Enclosure, which is kind of sealing, there are different types, and some of them, mainly, if you read the book, it will tell you that the main governing factor for deciding which way to go is either grease or oil and the speed. So this is the labyrinth seal, ya shabab, is very common in turbines and pumps, and if you go to Aramco, you will see it a lot because it is used for oil-based lubrication and for high speed. Similarly, there is also the matter of clearance. Do you know that if I zoom this in, I'm sorry, Shabab, I'm going to get late for 1 minute. This is a clearance that needs to be seized and closed in some application, especially when high precision and high speed is required. So how do you close that clearance? By preload. So they preload the bearing to close up this gap. Also, duplexing. It's called duplexing when you use when you use two angular payment, and look, you are here trying to orient them in a way where the thrust, because angular payment can handle the thrust, is resisted in one direction or cancel each other out. So this is also very important. I think I'm gonna stop here, and then inshallah next class we'll start chapter number 13. I'm gonna take your attendance now quickly, so I'll stop the camera and share my screen. You can leave right after when I call your names. Who do we have here? Yusuf Yusuf?
Yes, sir.
Al-Abbad Majid?
Yes, I'm here.
Hassan?
Yes, I'm here.
Abdurrahman?
Yes.
Muhammad Dabous?
The boss here.
Yeah, Dabous. Okay. Abdulaziz?
موجود.
محمد أحمد دوسري؟
موجود.
Abdullah?
Yes, alhamdulillah.
Khalid?
موجود يا دكتور.
مصلح?
موجود دكتور.
And we have Saud?
موجود.
Okay. Abdullah?
موجود.
الحجاب. Okay, where are you? I don't see you.
Yes.
Anyway, Salman. Okay, Salman was excused. Faris Jibrin.
Yes, دكتور.
طارق.
موجود.
عمر. مصطفى نويسر.
Yes, doctor.
عمر.
Yes.
لا العمر علي.
Yes, here.
خالد العتيبي. خالد.
موجود دكتور.
حسام القحطاني.
Yes, دكتور.
حسام. السادة.
Yes, here.
سلطان. نايف
Yes, here.
محمد
Yes, Doctor.
عبد الله الزهراني
Yes.
مشعل
موجود.
جعفر
Yes.
مؤيد
Yes.
علي
Yes.
and حسن شير.
Yes.
Okay, thank you so much يا شباب.